Welcome to Pioneering Possibilities, a series wherein we bring in bold ideas and bright minds to work upon sustainable future, circularity and energy efficiency. Now we know that energy efficiency is the first fuel helping customer to decarbonize the future. Sustainability, innovations, implementing solutions which help customer in reducing their greenhouse gas emissions is now getting good awareness in industrial premises, especially hard to abate sector. And when it comes to energy efficiency and sustainability, decarbonization, carbon capture, green hydrogen, fuel cells, the one and only one name comes in mind, that National Chemical Laboratories from Pune. I'm very happy to introduce you Dr. Lele from NCL, National Chemical Laboratories Pune. Dr. Lele is Director NCL. We welcome him on Alfa Laval podcast. Hello Dr. Lele. Sustainability, decarbonization, energy efficiency have been the key to drive towards a sustainable future. Can you please elaborate, help us understand the initiatives and actions done by NCL in this domain of sustainability, innovating solutions, helping customer in creating decarbonized future from NCL point of view?
Thank you, Snehal. First of all, I want to thank you for inviting me to this wonderful Alfa Laval podcast series. It's a real pleasure to be here, and I know some of the names that have already participated in this series, so I'm honored to be part of this program. And sustainability and innovation are two key words for NCL. They have always been key words for NCL. We'll start with innovation a little bit, because innovation to me is really a journey from concept to commercialization, as we call it, or from idea to impact. And if you look at NCL's charter, the motto of NCL, as was described by the Prime Minister in the inaugural ceremony of NCL so many years ago, 75 years ago, it talks about advancing knowledge and applying chemical sciences for the good of the people. And these are very profound, very simple but very profound statement, because it really epitomizes innovation. Because advancing knowledge is to move the frontiers, is to generate new knowledge, and the innovation journey starts from creating new knowledge. But you don't stop from creating new knowledge, you apply that knowledge. That means translating science into technologies, and that's the journey of innovation. You start, you do an innovation, and then you do a discovery, an invention, and then take that scientific discovery to translational stages to actual commercialization. So the journey of innovation is epitomized in NCL's charter, and we've been following that for a very long time. So that's my first thing about why NCL has been so interested for years in the innovation journey. Now coming to sustainability, which is your second part of it, and as you rightly said, this is absolutely the key thing for the planet today. And to me, sustainability has two things, two very simple definitions. If you consume less at a rate that is less than what the planet Earth can regenerate, that is the first definition of sustainability. The second is you don't leave residues at a rate higher than what the planet can assimilate. Okay, so consumption and release of residues, these two principles outline what sustainability is. And if you study these principles and stick to it, I think we will be in a much better state today, which means every innovation that you do, starting from invention to its translation, must follow these two principles, right? So keeping this in mind, and keeping the importance of sustainability in this decade, NCL's roadmap for this decade is really built on the foundation of sustainability and these two principles. So what are we doing today in this sustainability agenda? Some of the key programs that we have defined for NCL. First is clean energy. And within clean energy, we want to focus on green hydrogen and non-lithium batteries. Okay. Why these? Because these we believe are very critical for India from multiple perspectives. I'll touch upon those a little later. So first is the clean energy part. The second is circularity. Okay, and there we are focusing on circular economics of plastic waste, and that involves two components. Today's fossil-based plastic how can you make that more circular? So instead of one time use and throw, how can you take that plastic waste and recycle it back? Okay, so what are the technologies available for achieving that circular economy? The other component there is use as much biodegradable plastic, but keeping in mind that biodegradability also has a carbon footprint, and how do you minimize that so that the overall emission, the life cycle emissions as we call it, is kept low. So that's the two parts of the circular economy that we are today focusing on. The third agenda item on NCL's roadmap is to look at chemical industry in general, because we are a chemical laboratory. Chemistry is a big agenda for us, and working with especially the fine and specialty chemical industry is a key agenda for us. Now this industry involves pharmaceuticals, agrochemicals, dyes, pigments, flavors, fragrances, aromatic chemicals, construction chemicals, electronic chemicals. It's a huge sector. There are about 17 to 18,000 companies in India today manufacturing all of these chemicals. They contribute about 7% of India's GDP and emit about 60 tons per annum of CO2.
Very large number.
Very large amount of CO2 emission. And since we are very deeply engaged with this industry sector, it is important for us to say how can we decarbonize that sector, and not just decarbonization, how can we reduce the solid waste coming out of it and the zero liquid discharge. And I know that both of these are very dear to Alfa Laval's heart as well. So decarbonizing the Indian chemical industry is the third big thing that we are doing. As a subsector of that, we want to also bring in more and more biomanufacturing, okay? Because many of these chemicals are manufactured at high temperatures. There's a lot of energy inefficiency associated with heating, cooling. Whereas if you mimic nature, where nature operates at ambient temperatures, at ambient pressures, right? So can you use the way that get inspired by nature? Can you use what nature uses, which are basically biocatalysis, enzymes, microorganisms that do all the chemistry within them? Can you harness that power of nature and substitute chemical processes by biomanufacturing processes? So that's the fourth thing that we are very deeply engaged into. So among the NCL agenda, the roadmap that we have for this decade, from a sustainability point of view, these are the 4 or 5 things that we are very much focusing on today.
Very well said, sir. Very well said, sir. From your discussion, I take a couple of points. Hydrogen, you mentioned about decarbonization, sustainability. Now, we as a India, we are a developing country. Our net zero is 2070. But when you look at Alfa Laval, we are a European company. Our roots are in Europe, Sweden. Our net zero year declared is 2050 and carbon neutrality was 2030. When I say was, means that we have worked on scope 1 and scope 2 and scope 3 emissions, taken a lot of actions, and now we are proudly mentioning and saying to the world that even though declared year was 2030 as carbon neutral, but we would be carbon neutral by 2027. So we are helping our customers in their sustainability goals with Alfa Laval heat transfer solutions, separation solutions, fluid handling solutions, zero liquid discharge, and a good contribution in green hydrogen because we are member of European Hydrogen Council. We help the customers on PAM, alkaline, SOEC, anion exchange membrane, and we perform heat integration and cooling part. So in India, we are very much helping customers for their transition to net zero. 2070 net zero India. Now when I look at NCL, how NCL contributes to India's transition towards net zero by 2070, what is NCL actually doing for this contribution?
So see, NCL is a research and development laboratory, right? Which means we can develop new solutions, new technologies, but the actual implementation at scale ultimately has to be done by the industrial sector. So we have a contribution in terms of the inventions, and helping the industry through the innovation or the de-risking journey, right? We continuously work with them, handhold them in the scale-up journey as well. So whatever technologies we develop and license to our clients, we don't stop at licensing bit. We work with them through and through, and that journey actually is a difficult journey because it's classically called the valley of death. A lot of technologies which might look like very good technologies at a lab scale may fall down in the valley of death and die because there could be many hurdles that come in the scale up, the prototyping journey. Some of them are technical difficulties, some of them are commercial market forces determined difficulties. But we try as a laboratory to help the industry work shoulder to shoulder with the industry to help this journey of lab to market commercialization. Okay, so that we believe is our contribution to India's net zero. So biggest contribution from us is the innovation part, because we bring in new technologies. And when I say we bring in new technologies, we want to focus on the end-to-end bit of the technology. So just to give you an example, if you look at an electrolyzer or a fuel cell, the low-hanging fruit today is to harness the existing power of India, right, which is great process engineering. I think we are excellent in process engineering. We are excellent in electronics and electrical systems. So in an electrolyzer, for example, the whole balance of system, right, which is the all the heat exchange that Alfa Laval is good at.
In fact, the heat rejection arrangement, chillers,
Correct,
and
correct.
the BOP content of any electrolysis process.
Absolutely. So all the BOP part and the power electronics part that India is very good at, and that's a low-hanging fruit for India, which means you buy stacks from outside, you integrate them in the balance of system, and you run the electrolyzer, right? It achieves the goal of producing green hydrogen.
Green hydrogen.
But we still become dependent on the core technology,
the stacks,
which is the stack. Okay, and that's where we would like to come in. Okay, because what is a stack? It's basically electrochemistry, right? And chemistry is where we play, right? And therefore we want to get into that core technology, break it down into all the subsystems, the advanced materials that are used, and see how we can develop that core technology, which is differentiated, which means it has to be IP protected, it's new, it's novel, there's a component of novelty in it, and also develop an ecosystem and manufacturing ecosystem which will manufacture the raw materials, which will manufacture the subcomponents and the full stack system. Okay, that's where we would like to play in, and I believe as a R&D lab and also a chemistry focused lab, to focus on the core technology of a stack, whether it's an electrolyzer stack or a fuel cell stack, that is where we would like to focus on, right, and bring that technology to India with the ecosystem of manufacturing. That's, I think, so we do this for other parts also. Let me give you another example. We work very closely, as I said, with specialty and fine chemical industry. And one of the things we are doing there is to help the industry move from batch processes to continuous processes. Okay, in the continuous process, you're doing the same chemical reactions, but with a great advantage. There are multiple great advantages, whether it is safety, high conversions, better selectivity, better heat exchange capabilities, and so on. Now in that, the innovation is really the reactor part. So again, the core part of the technology, not the piping and valves and so on. The core is the reactor. Okay, and many of these interesting reactors look like your heat exchangers, for example. They have the same kind of geometry. Now again, one can import the reactors into India, but that is not our objective. We want to create a manufacturing system in India which will do core manufacturing, core technology manufacturing. So these are the examples that I am trying to give you. How do we help industry in this whole journey of achieving carbon neutrality or net zero? Invent and make sure you create the whole ecosystem for all that core technology that goes behind that invention. Okay, and thirdly, help the industry clients in the journey for lab to market. These are our contributions, I believe.
Very well said and perfectly understood, sir. Green hydrogen is going to be a game changer, helping the industry in creating a decarbonized future. And your work in fuel cells and green hydrogen, really, hats off. Very great, sir. Very great.
We have had a very interesting journey in fuel cells. Our journey started back in 2002. That is more than 20 years ago. India at that time was not talking about hydrogen, but we believed that a clean energy vector like hydrogen is going to be important for India, even at that time. Many times we were laughed at, saying hydrogen is the next generation fuel, which means that it will always be next generation fuel, right? But we believed that hydrogen will become important for India for very simple reasons. You need good sunlight, you need a lot of water to make hydrogen, and India is blessed with both of these primary sources. We have great sunlight, we have great monsoon. If we can capture our water better and use it better, and use technologies such as what Alfa Laval brings,
fresh water
generation through good heat integration.
Correct.
Right? If we do that, I think India has enough water to generate hydrogen. So therefore, we believe that hydrogen is going to be important for India right from 2002. And our whole journey in developing the fuel cell technology started from the lab, small fuel cells we used to make. And I'm very proud to say that today that journey has, with our industry partner, of course, which is a very key component in this, we have managed to take these small fuel cells that we used to make in the lab into full prototypes, which are integrated with the drivetrain. And today we have India's first fuel cell car, first fuel cell bus, and first fuel cell powered catamaran. All of these are real prototypes that have been fully tested on the road, in the water. So this journey from lab to near commercialization, along with industry partner, has been a very fruitful and a rewarding journey for us, and we take great pride in doing that. In India, I believe this whole journey of lab to market has just now started. So we are very happy about it.
Very nice, sir. And you rightly mentioned, actually green hydrogen is going to require huge amount of ultra pure water. If you think that much ultra pure water is not available, but there are technologies, what we just now discussed, electrolyzer is going to heat up. If you recover the heat, electrolyzer will cool down, and we can do thermal desalination of black water, sea water, and generate ultra pure water for electrolysis. Now, we keep on hearing that government has to do something in green hydrogen. They have to push, they have to prove, they have to set up some examples in green hydrogen. There are some private players who are setting up green hydrogen through alkaline electrolysis. They have tie-ups and collaborations with foreign companies, and they are trying to build something in India. But when it comes to government, one thing comes in mind: Government of India, NCL being a government entity. We keep on hearing about hydrogen valleys. Can you please throw some lights on hydrogen valleys? How they are going to perform? Where these valleys are going to come? Who would be the consumer of this green hydrogen produced? Whether this green hydrogen would also be used in some sort of transportation, because we discussed that mobility is highly polluting, maybe 12 or 11% you mentioned that CO2 emissions. So please throw some lights on this green hydrogen valleys. We have been hearing. Our audience would like to know more about green hydrogen valleys. How many, where, when, and definitely NCL's role in this.
Right. No, that's very interesting question, because I'm so enamored by this hydrogen valley concept. The reason is the following, that there has been a lot of talk about how to take technologies from lab to commercialization, and NCL has been doing it with some successes, some failures. That is part of the journey. But I think India needs new models to take discoveries from the lab to market. And I talked about valley of death, right? You need new models to bridge this valley of death. One of the model is to bring many partners of the ecosystem to collaborate and work together. Okay, and that's really the genesis of a hydrogen valley. So what is a valley? Hydrogen valley is a concept where all parts of hydrogen value chain technologies whether it is production of hydrogen, storage of hydrogen, distribution of hydrogen, utilization of hydrogen. All of those have to be demonstrated within a certain geographical region to show that yes, it is possible, and not at a laboratory scale, it is actually possible at a semi-commercial scale. Okay? The whole hydrogen value chain demonstrated at a semi-commercial scale is the genesis of Hydrogen Valley. Okay? Now, it's not just a demonstration. There is a sustainability part of in the Hydrogen Valley, which means that these technologies is not like a small prototype that you just show and wind up. These technologies have to run for 5, 10, 15 years, okay? Which means there's a financial sustainability part also in it, because nobody is going to burn their money for 15 years. You have to be financially sustainable as well. So the Hydrogen Valley concept is not just a technology demonstrator, but it is a techno-economic demonstrator. So what does this concept achieve? It achieves a lot of collaboration between various partners, because no one industry can play in all parts of the hydrogen chain. There will be some industry which will get into production of hydrogen, some industry storage of hydrogen, distribution of hydrogen, utilization of hydrogen. So which means you are getting multiple industry partners to collaborate for one objective, and that objective is to do a technology demonstrator and a techno-economic demonstrator at a semi-commercial scale. Right? Now this is a new experiment in India. It has not happened many times in the past, right? And so this is, I think, in a clean energy sector, in an upcoming sector like green hydrogen, this is one of its kind experiment. So when the government...
If I may ask you, what would be the capacity of any of this valley?
Right. So each valley is asked to produce at least 2 tons per day of hydrogen, green hydrogen. 2 tons per day.
To start with, it's a good quantity.
It is a reasonable quantity. 2 tons per day is a reasonable quantity, right? What the government did, and this is through the Department of Science and Technology, which is part of the Ministry of Science and Technology. And they said, we want to create hydrogen valleys, right? This was never done in India. So this was a first time idea of creating hydrogen valleys. And because it was first time, nobody really knew how to do this, right? So we had a lot of brainstorming sessions with the DST, the Department of Science and Technology, to conceive this whole process. How do you create such a hydrogen valley? How do you bring partners together? How do you operate the valley? How do you select technologies? How do you make sure that financially there is a reasonable sustainability, right? And at 2 tons per day, which is a semi-commercial scale, I would say. It's not a full-scale commercial, right? We're not talking of gigawatt scale electrolyzers here. We're still talking
But still 2 tons per day, you mentioned fine chemical and specialty chemicals.
Right.
They are the consumers of this.
That's right. So 2 tons per day is about, let's say from an electrolysis perspective, about 6-7 megawatts of electrolyzer, right? So it's not gigawatt scale, but it is not lab scale. It is somewhere in between, right? To bring financial sustainability to this is a key point. To bring financial sustainability to a 6 megawatt kind of electrolysis system, the government support is required from a financial support point of view. And so with the DST, we said that we have to the government has to put in a viability gap fund, which provides an impetus to make this whole project reasonably financially sustainable, which means roughly about 30% of the financial support comes from the government and 70% comes from the industrial partners. Okay, so there is a bit of a support given by the government to make this project financially viable, right? And I think this kind of support for new technologies is very important, and all over the world this kind of financial support from the government has happened, and that has pushed the change from incumbent fossil carbon emitting technologies to the new clean green technologies. This push is very important. So with this lot of thinking, the government invited proposals. They said, who wants to pitch for a hydrogen valley? And you will be surprised, about 100 proposals came to the government. So you can see the interest in India. A lot of institutes, companies,
awesome.
A lot of institute companies came together, right, and said, we want to create hydrogen valleys. Then of course there was a lot of due diligence done by the government. Several committees were appointed to look at every proposal and see the technology, the innovation in the technology, and the financial viability of these projects. Based on all those discussions, 4 hydrogen valleys were finally selected.
Okay.
And they are strategically located at 4 corners of India. Right? So there is one in Bhubaneswar, there is one in Jodhpur, north, there is one in Kerala, south, and I am very happy to say that there is one in western part of India, which is in Pune. So we call it the Pune Hydrogen Valley, and this was conceived by NCL along with the Pune Knowledge Cluster. So PKC and NCL joined hands to conceive this whole idea of Pune Hydrogen Valley. Now the Pune Hydrogen Valley, we are very excited about it because it has 2-3 innovative components in it. First of all, the production of green hydrogen is done by 2 processes. We are going to use a small electrolyzer, not a very large electrolyzer. We will use a 1 megawatt electrolyzer to produce about 300 to 330 kilograms per day.
And that would be alkaline or PEM?
We will choose the right technology. It will be either alkaline or its cousin, which is the anion exchange membrane.
AEM we call that.
AEM electrolyzer is interesting. It's sort of a new kid on the block in the electrolysis segment. I am interested in it due to a little bit of selfish reason, because we in NCL are developing AEM technology. Doesn't mean that our electrolyzer will go there, but we will be looking for either good alkaline electrolyzer or a good AEM electrolyzer at a 1 megawatt scale. Okay. So that's the electrolysis part. But remember, our production demand is 2 tons per day, and the electrolysis 1 megawatt, it will only give 330 kg per day.
I was about to mention that.
The remaining 1.7 or 1.8 tons per day, we are going to use a completely new technology. Okay, and this is again in the valley. This is what the valley is supposed to do: take a technology which is innovative, which has come out of an academic environment, and scale it up to commercial, semi-commercial level. This is the valley of death. This is what the hydrogen valley wants to achieve. So we are looking at a very innovative technology which in a 1-step catalytic process converts bioethanol into ethyl acetate, and a byproduct of this process gives you hydrogen. So what are we doing in this technology? We are taking bioethanol, so it's a renewable chemical.
Yes.
Which is widely available today. You know, ethanol is used in as a substitute in petrol, as an addition in petrol. So bioethanol is available in a variety of distilleries, in sugar industry. A lot of ethanol is available. We take some of that ethanol and, as I said, convert it into ethyl acetate. Okay, ethyl acetate is a widely used solvent in fine chemical industry. Very widely used. In India today, we import about 3,000 tons per month of ethyl acetate. We are importing today. We are making ethyl acetate, but we are importing 3,000 tons per month of ethyl acetate. And hydrogen comes out as a byproduct. There is no other byproduct in this. So it's just hydrogen and ethyl acetate. And since we start with bioethanol, and we've done all the carbon emission calculations, the amount of CO2 emission associated with hydrogen. So if I take this process and whatever emissions are there, CO2 emissions are there, I load all of that on hydrogen.
Still, as per our local norms, the
it is below
CO2
that,
per kg,
absolutely
2 or something?
It is, in our calculation shows it's less than 1.85 kg per kg. Okay, it's less than 1.85, and it's a conservative estimate. And I know how I can bring it further down to 1.4, 1.5 kg per kg. So it's well below the Indian norms of what is green hydrogen.
As per our norms, it's a clearly green hydrogen.
It's a green hydrogen. And as I said, we can bring the CO2 emissions down further. Now the interesting bit here is this is a technology where you get hydrogen and a byproduct. Now look at electrolysis. You also get hydrogen and oxygen as a byproduct.
Yes.
So many of these routes to generate hydrogen actually gives you a byproduct. The financial viability of these processes depends on how you valorize, how you monetize the byproduct. In an electrolysis process, there are not too many options for valorizing oxygen. So if you look at most of the electrolysis plants that are coming up in this country today or in Europe, oxygen is just vented out.
I am seeing some examples wherein oxygen is literally vented out.
Is vented out. because the market prices for oxygen are not that great. You have to take that gas, compress it, bottle it, transport it. All of that is expensive, right? Ethyl acetate, as I said, in the main product that comes out of our technology.
And again, hydrogen is a byproduct.
Hydrogen is a byproduct. Ethyl acetate is the mass wise, mass quantity wise, ethyl acetate is the bigger component. Hydrogen is a byproduct. That ethyl acetate is a liquid, easy to store. You don't need compressed gas storage, easy to transport. Because it's a liquid and already ethyl acetate is being transported, so we are not inventing anything new, we are using current supply chains. That ethyl acetate has a great price in the market today in the fine and specialty chemical industry. So we are targeting the fine and specialty chemical industry as an end user for two reasons. One, they use ethyl acetate and they use hydrogen. Hydrogen is used as a reducing agent in the fine chemical industry. You go to any pharmaceutical hub like Hyderabad, you go to any fine chemicals hub like Gujarat, Ankleshwar, Dahej, Panoli, Saika, you go to any fine chemicals hub like Taloja, Kalyan region, right, or Solapur, they are all using hydrogen today. All that hydrogen today is used for hydrogenation reactions. It's a feedstock. And today that hydrogen is a grey hydrogen. It is coming from chloralkali plants. You will be surprised how much that hydrogen travels in this country. It is produced in a chloralkali plant somewhere in Gujarat, like let's say Dahej, and then it goes all the way to Solapur, it goes all the way to Mumbai, Taloja. So that grey hydrogen is further emitting
CO2
during the
while
transportation. Right? Can we substitute that grey hydrogen with green hydrogen at the same price point? That is the challenge. Okay?
The generation near the consumers.
Exactly. So we are trying to set up this plant, this in the Pune Hydrogen Valley, not very far away from the consumer. And so we are targeting the chemical belt either in Pune near Kurkum or in Taloja, not too far away from where we are planning to set up the Hydrogen Valley. Okay, it's less than 100 kilometers. And there is already supply chains for hydrogen transportation that exist. So we are just going to use those supply chains. So that is the point. Now, why fine chemical industry? I already said earlier that it's a big industry in India. About 17,000 plus companies are there in India today. It's a very big sector and it emits a lot of CO2. Interestingly, about 65% of these products, these chemicals that are made by this sector are exported. Look at pharmaceuticals. About 25% of generic drugs sold in Europe and North America come from India. Now, if you use green hydrogen and any such green chemistry to make these molecules, you immediately get carbon credits in those markets outside. Those carbon credits will hopefully come in India as well. I don't think that it's too far away now.
I was reading something, 1st January 2026, CBAM would be the reality.
Exactly. Right, and that will then extend to not just steel, but it will extend to everything today. So if you use green chemicals such as green hydrogen in the production of these chemicals, I think there's a great advantage for India. So we are tying up a new innovation, bioethanol to hydrogen, with a new usage, which is fine chemical industry. And that innovation chain is what the Pune Hydrogen Valley is very excited about. So that's what we are doing.
It's a really good going discussion with you. We know now in India, NDCs are in place. National Green Hydrogen Mission is driving India. So many technologies are coming, developments are happening, commercial projects are coming. So we all are there to support the industry to become more and more energy efficient. Another thing what we have been seeing is that in addition to green hydrogen, semiconductor industry is picking up. So semiconductor mission India in place, a lot of developments are happening. Now 1st Jan 2026, CBAM will come in place. At the same time in our country, business reporting, sustainability reporting is already there. People are now aware about capturing the carbon dioxide because hard to abate sectors are the biggest contributors for CO2. So when it comes to CO2 emission from these big industries, CCUS and CCU comes in picture. we have been helping this industry in capturing process more and more energy efficient with our heat transfer solutions from Alfa Laval. And we have been seeing some projects in India, but still this industry needs backing from institutions like NCL. So would you like to throw some light on carbon capture, CCU and CCUS from NCL point of view?
This is the biggest and the most difficult problem today. CCUS is absolutely critical. Let me say that in the beginning. For India to reach its NDCs, the net zero by 2070 cannot be done without CCUS. I think it's the most difficult task. It's even more difficult than green hydrogen in my opinion. Because as you rightly said, hard to abate industries, whether it is steel, cement, power sector, refining, ammonia, huge emissions come out of these. Steel at least 2 tons per ton on an average, 2 tons of CO2 per ton of steel. Cement about 0.9 tons of CO2 per ton of cement. So huge emissions come out of this. Unless these emissions are curtailed, they are captured, India will not reach its net zero targets. Okay, so the next big thing that India needs to do as a country is a serious investment in CCUS. And like in hydrogen technologies, these technologies are not really truly mature at commercial scale. And I think India today is taking these big risks. In the past, we used to wait until these technologies matured in the world and then we would simply buy them. Today, we do not have that luxury. We have to do CCUS now.
Actually, we don't have time as well.
We don't have time. That's why I said we don't have the luxury to wait until these technologies mature outside and then buy them. We have to do that innovation here in India. We have to do the scale up here in India. And that's the challenge. But I think the government is up to it. The government has fully realized it. And we are hoping that something big in CCUS at India level will come up. In the CCUS value chain, the biggest difficulty is to capture carbon, because most of the emissions come out of a stack, what we call an end of pipe emissions. So you have a steel plant, it's running, and out of the stack comes out gases, off gases, which are about 10%, 9% CO2 concentration, a very dilute stream of CO2. And that CO2 is in millions of tons, right? And that has to be captured. So the challenge is to take a dilute mixture of gases coming out at a fairly high temperature, containing only 9-10% CO2. On the whole, it's millions of tons. That's how much gas is emitting from it, and capture that CO2, right? And it's fantastic to see Alfa Laval's technology that not just helps capturing the CO2, but helps use the heat. And that heat is very important, Snehal, because in a typical carbon capture plant coming out of a stack gas, right? It's not the capture that is so difficult, it's the regeneration that is more difficult. That is, let's say, typical technology is an amine technology. You use a concoction of very high value amines, which will capture CO2 very effectively.
Yes.
Now, how do you take that amine back? Because it's a very strong bond between the amine and the CO2. Amine is a base, CO2 is acidic. So it's an acid-base reaction essentially, right? And that reaction is actually a little bit of exothermic reaction, right? It happens very fast, releases a bit of heat. That heat needs to be captured, because ultimately you have to take that amine and recirculate it back. You can't throw that amine CO2 adduct. You have to separate.
It remains
again.
in cycle.
It remains in cycle. So the CO2 has to be taken out and the amine has to be recycled. The reverse reaction, which is how do you separate amine from CO2, the reverse reaction requires heat. So in the first reaction where you captured CO2, you are liberating some heat. In the second reaction where you want to liberate that CO2, the captured CO2, you need to supply heat. Now if you don't do heat integration, then the amount of heat required to release the CO2, if that heat comes from another carbon emission plant, the overall amount of CO2 that you are releasing is far more than the CO2 you are trying to capture. So it will never be net CO2 zero. Therefore, heat integration is a very critical part of the carbon capture, and it's the regeneration of amine which is the more difficult part. So it's very heartening to see that a company like Alfa Laval brings its finest
That's a pride
technology.
for us. Actually, we are pioneering the heat integration and waste heat recovery.
Yes, and I think in India that will be required in a very, very large scale. Okay, so of course there is a lot of innovation that happens in how do you reduce the heat required to release the CO2. Okay, and that's where it's never one amine, it's always a mixture of amines. The purpose of that mixture is to reduce the overall heat required to separate the CO2 from the amine. Nonetheless, whatever amine you use, heat integration will be required. There are other methods of carbon capture, and some of those methods are interesting and perhaps low-hanging fruit for India, where you can capture the CO2 and make a product out of it. So there is a nice innovation that a young professor at IIT Bombay has been developing, which captures CO2 and mineralizes it. It converts into a valuable mineral like calcium carbonate or magnesium carbonate. These carbonates are very high value added product. You don't need to separate the CO2 from it. The carbonate itself is sold as a high value product. So you take this stacked gas, off gas, and you capture the CO2 and make a product out of it. So we have to look at all of these kinds of new technologies that are coming for carbon capture. What is NCL doing? NCL is looking at downstream of carbon capture. So once you have captured CO2 and once you get a purer stream of CO2 coming out of the carbon capture plant.
Yeah, because that is the biggest hurdle for industry. What do we do with that captured CO2?
Correct. So carbon capture is only one part of the solution. It's not the ultimate solution. Of course, if you mineralize it, then you have fixed the carbon. Right? And you have sold a good product. But you can't convert all the millions of tons of CO2 into a carbonate, because that's not the market available for carbonate. You have to do something with that CO2. Now, there are two things one can do with the CO2. One is you can convert that CO2 into a value-added chemical. So, for example, today one of the most exciting technologies that people are looking at is converting CO2 into methanol. So you take CO2, you take green hydrogen, you react them and you make methanol out of it. It's exciting because India needs a lot of methanol. You will be surprised how much methanol India is importing today. 95% of methanol that is used and consumed in this country is imported. 95%. So India wants methanol. And what could be more exciting than taking that CO2 and converting that into methanol? Methanol is a feedstock. Once you have methanol, you can make a whole variety of materials and chemicals out of it. You can of course burn methanol as a fuel, but that would not serve the purpose because you are releasing CO2 again. It would be better to convert methanol into something which is permanently capturing the CO2 for a long period of time. For example, methanol can be converted into olefins. So there is this technology called M2O, methanol to olefin. Once you have olefin like ethylene or propylene, you can convert ethylene, propylene into a variety of chemicals or variety of materials, and the biggest we all know is polyethylene, right? So you take CO2, convert to methanol, methanol to olefin, olefin to polyolefins. You have fixed the CO2, right? So it's very exciting, but there is always a but.
Cost economics?
Cost economics is always an issue. So green hydrogen is required for converting CO2 into methanol. So the first challenge is, can you make green hydrogen at a
viable
price point? Exactly. And that's where the Pune Hydrogen Valley that we talked about. If technologies like those can be discovered to make hydrogen at a price point which is exactly the same as green hydrogen, gray hydrogen today, then you have hydrogen available at the right price point. Now still, even if hydrogen is available at a reasonable cost, there is still a challenge of converting CO2 into methanol, because CO2, if you go back to basic thermodynamics, CO2 is a very stable product. In thermodynamics, we call something called as free energy, right? The lowest point of free energy is where CO2 sits. Which means if you have to do something out of CO2, you have to make something out of CO2, you have to supply energy. Because it's sitting at the valley in the lowest point of free energy, you have to supply energy to make it reactive, right? So CO2 is a very stable molecule. You have to provide heat energy, electrical energy, some form of energy to convert it into methanol. Again, if you need heat energy, and if that heat comes from fossil fuel, you will emit CO2.
There's no purpose, yes.
Right. So again, you have to use renewable energy, you have to use more energy efficient processes to convert CO2 into methanol. And that is what NCL is trying to discover. Are there new novel catalysts that will use less energy, less heat energy, less electrical energy to convert CO2 into methanol? Today, CO2 to methanol conversion would require about 250 to 300 degrees centigrade. Can I make CO2 to methanol at 100 degrees centigrade?
Half of the energy, thermal energy.
Half of the heat energy required. Today, CO2 to methanol requires 50 bar pressure. You have to compress CO2 to 50 bar. So again, mechanical energy required for
electrical
compression.
Energy, again fossil fuel linkage with this.
Can you do this reaction at 10 bar pressure, 1/5 the pressure? So that is the challenge we set ourselves. Again, we come from a chemistry background, right? We are very good in catalysis. Can we discover new catalysts that will reduce the overall energy required to convert CO2 into methanol? If this can be done, it would be a game changer. We've done the math, we've done the economics. CO2 to methanol conversion with grey hydrogen coming at the right price point, we can make methanol today at the same price that we are importing methanol. Again, from a supply chain resilience point of view, an Atmanirbhar point of view, this is very critical. So CO2 conversion technologies are very, very important for India, and it requires fundamental discoveries to happen in the field of catalysis to convert CO2 into something value added. Okay, we are also looking at completely new ways of using CO2. For example, you can use, instead of heat energy, you can use electrical energy. You can use electrons to do the reduction. Instead of using a molecule, you use electrons to do the reduction. That reactor where this reaction would happen, it's an electrochemical reaction. It looks like a fuel cell. It looks like an electrolyzer. So can we use our knowledge in fuel cells, in electrolyzers, and bring that here, right? So you are connecting dots. You are bringing some knowledge from an outside domain and using it to do a reaction, which is a little different. So those are the kind of innovations that we want to put our attention to at NCL. So it's the CO2 conversion part that we are deeply engaged in. One of our sister labs is doing the other bit, which is actually very key. No matter how much CO2 you use or convert, there is lot more CO2 available than how much you can convert into a methanol or something else. Because methanol market is limited. CO2 emissions are way higher than that. So you have to do something with the remaining CO2, right? And really the only truly required thing today to be done at large scale in India is find ways to sequester CO2, to convert, to pump it down in geological strata where nature will fix it. Okay, so that's the sequestration part, the storage or the sequestration. So CCUS, the S bit is the storage bit, and this really is very difficult. It requires us to find geological strata where CO2 can be pumped and stored in a very safe manner, because it is fraught with many risks. You could have plumes of CO2 formed in an underwater reservoir. Those plumes can migrate, those plumes can escape, right? And you don't want any of that to happen. And that requires a lot of geological science. And that's where some of our labs in CSIR or in IITs are working closely with industry to figure out where are those locations in India where CO2 can be stored underground, whether onshore or offshore, safely, without the risks associated with it, and also monitor it continuously. Just like you monitor your heat exchangers or compressors, we have to monitor the CO2, it's what is happening to that CO2 underground. So this is actually very critical for India, and a lot of investments are required, and that's where I think a national level mission for CCUS is the need of the hour today. It's a huge need of the hour today.
This is becoming very interesting discussion with you, and the applications are many. Reduction in pressure, energy saving. Reduction in temperature, again energy saving. Undoubtedly, NCL is playing very important, vital role in this journey. So, Dr. Lele, while working on carbon neutrality, net zero, we as an organization who is into heat transfer and separation are completely confident that the world is moving towards greener future, because the organizations like NCL, Alfa Laval are putting their efforts day in day out in terms of making the energy industry most and most energy efficient. There are challenges, but there are many opportunities as well.
Yeah.
And when we think of challenges, actually industry need to know the technologies are in place and they should inquire, share their problems. The companies are there to support them in terms of process cooling, process heating, waste heat recovery. We talked about carbon capture, hydrogen, heat integration in a hydrogen plant. What is the most best that save and utilize each and every kilocalories?
Yeah.
Stacks are heating up, cool it, do thermal desalination, get ultra pure water, or say carbon capture. So technologies are in place, challenges are there, opportunities are there, and we as organization Alfa Laval helping industry in their sustainability goals. You as a Government of India organization innovating, developing newer and newer technology. Just now we spoke about temperature reduction, pressure reduction. So these challenges what industry is having, moving forward towards a energy efficient decarbonized future. And when we specifically speak about energy efficiency, as per you, how NCL is going to support in terms of addressing the challenges, and what are the opportunities going forward?
So Snehal, energy efficiency is in my opinion, a low-hanging fruit, right? Because you don't have to change the entire technology. You have to do retrofits, a better heat exchanger, a more process intensified condenser, right? So you're not changing the technology, you're bringing in components which will increase efficiency and therefore reduce the carbon emission, right? So I think these are very important low-hanging fruits that we must adopt. Energy efficiency is the simplest thing that we should do. At national level, this has to be done, okay? And a good example of that is in India, one point of time we used to use CFL bulbs, before that filament bulbs, and they're extremely highly inefficient. Today we have very quickly moved to LEDs, right? And there is innovation, both technology innovation, moving to better sources, more efficient sources of harnessing electricity and converting into light, and LED is a good example, and also other innovations which are more business process innovations, such as public procurement. So we have seen how India transitioned from CFL to LED, and that one transition, which is an energy efficiency transition, has considerably reduced the emissions from India. So like that, in almost all industries, as you very rightly said, if they can use better heat exchangers, they can use better evaporators, they can use better condensers, better filtration techniques, that will add very significantly to lowering the carbon emissions. But beyond that, we still, in order to achieve our targets for net zero, we have to invent new technologies also. At some point of time, we will have to do big changes in the technology. For example, instead of using carbon to reduce steel, can we use hydrogen to reduce steel, green hydrogen to reduce steel?
DRI steel.
DRI steel is an example. So moving from pure coke, which is used today to reduce steel, moving from coke can be moved to syngas, which is a CO hydrogen mixture, right? And from syngas, which is the DRI process, from there can we use pure hydrogen. Now these are significant shifts in technology. We will have to do some re-engineering of the processes around blast furnace to make this happen. It's not easy to simply replace carbon with hydrogen, right? These are the big changes that have to happen in order for India to reach its 2070 net zero goal. So we need to make new changes to technologies, such as in cement plants. The technology for how we make cement has to change significantly. Therefore, for these changes to happen, significant R&D investment is required. You look at India's R&D investment today, something called the gross expenditure for R&D, GERD is the word. If you compare India's GERD with other developed countries, let's say US or China, the GERD today is about 2 to 3% of the GDP. Okay, in some countries it is as much as 5% of the GDP. So countries are investing very significantly into R&D. India has been stagnated at about 0.6, 0.7% of GDP.
So in comparison with them,
It's much lower.
Much lower.
And therefore, if India has to achieve its dream of becoming a Viksit Bharat by 2047, GRD is one of the important metric of being a developed country. How much of your GDP are you investing in innovation? That is the GRD. That has to grow in India. Now, more importantly than that, even in today's GRD of India, if you see how much is the government investing in the R&D and how much industry is investing in R&D, the industry investments are a meager 35%, 35 to 40%. Compare that with US, compare that with China, compare that with Japan, the industrial contribution is between 75 to 80%. So the amount of expenditure that a country or investment that a country is doing in R&D, 75 to 80% of that comes from industrial contribution and lesser from the government. In India, the ratio is flipped. So that also needs to change, right? So the quantum of investment in R&D and the industrial contribution to R&D both has to increase in India if it really and truly has to become a Viksit Bharat. And I think that to me is one of the biggest challenges in India today. How do we make this transition to happen? And I think a great catalyzing factor that the government has now introduced is what is called the ANRF. You must have heard about it, the Anusandhan National Research Foundation. It's a big step that the government is taking, and the biggest task for ANRF today is to get public-private partnership to happen and to get more and more industry to contribute to ANRF funding, research funding. And I think the ANRF is doing great, and the vision that they have, the plans that they are coming out with, they are all catalyzing this industry academia collaboration and industry investment in R&D. It's time that the industry takes this opportunity, this ANRF as an opportunity, and starts real investments in R&D, because let me reiterate, without significant investment in R&D, India will not achieve its net zero vision by 2070. This has to happen. There are other challenges, and one other important challenge is in this VUCA world today, India has to be self-reliant. There is no option for us today, unfortunately. We believe as a country in globalization. We have always believed in globalization. We have always believed in that understanding of a globalized world, as the world together becoming green. But today's geopolitics are such that we are forced to become more and more self-reliant. To do that, we have to we have to develop our own technologies. We have to do a lot more manufacturing in this country today. Our manufacturing contribution to GDP is hardly 15-17%. that has to significantly grow, right? And for manufacturing to grow, we can't be dependent on raw materials coming from some other country into India. We can't be dependent on energy imports into this country. So increasingly, self-reliance, Atmanirbharta is the second big challenge for India today. Okay, and again there, the R&D institutions like us and in industries such as Alfa Laval and the large manufacturing industry have to work together and make this self-reliance
collaboration is key to success.
Is absolutely the key of today. So R&D investments and collaboration to bring more self-reliance, Atmanirbharta in the country are the two biggest challenges today. You asked about opportunities. So there's challenges, and every challenge is an opportunity. And I believe that what is lacking in this country? Nothing is lacking. We are as a Indian population, we are a very innovative culture. Innovation is in our blood. You go and find, even a vendor who's telling something on the street is innovative, right? I mean, where else in the world will you see a sabji wala on the street with a QR code on, right? I mean, this is innovation, and adoption of innovation is, I believe, in our blood. We are an entrepreneurial country. We are innovators. And look at the youth of this country. The demographic dividend of this country is phenomenal. I mean, we are a young country. We are the youngest country in the world today. Large population and young country, right? And all of them are innovators and entrepreneurial in nature. What more do you want, right? We want to capture and harness that innovation, bring that into mainstream, infuse resources, invest in R&D, and I think India's future can only be bright. But we need to make this happen.
Excellent. Big takeaway from this discussion is that collaboration and partnerships is going to drive the successful future. And this way of working together will actually help the industry in creating a decarbonized future.
Yeah.
So once again, thank you for visiting Alfa Laval. It was very nice discussion with you, understanding your thoughts, your ways on carbon capture, green hydrogen, energy efficiency, investment in R&D, and let's hope that soon we will have the success on your carbon capture way, wherein the reducing temperature and pressure will help the industry in reducing the fossil fuel consumption. And wish you all the best. And thank you once again for being on our podcast.
Thank you, Snehal, for this great opportunity. It's been wonderful discussing with this, and wonderful to be at Alfa Laval and see all your innovations. Let's NCL and Alfa Laval have a new way of collaborating in both green hydrogen and carbon conversion space. Thank you very much.
Namaskar.